In Part 2 of Lecture 7, we will discuss deadlock prevention and deadlock avoidance. How do we handle deadlock? For all practical purposes, we can either prevent it, detect it when it happens, and then recover from it, or simply pretend that it never happens. Many operating systems take this last approach, which is not without problems. There is a story of one system that was shut down, and they discovered on it a process that had been waiting for 10 years. Ignoring deadlock can potentially lead to situations just like that one. Preventing deadlock, in theory, is simple. Prevent one of the 4 necessary conditions from becoming true. The most immediate problem is that you cannot prevent the first condition in most instances where you find it. The only way to eliminate mutual exclusion is a hardware solution. Increase the number of devices, but not even that will always eliminate mutual exclusion. Another possibility is to prevent processes from holding resources while they wait for other resources. This prevents the hold and wait condition. We can require that a process that was denied a resource give up the ones that it is holding. This adds the possibility of preemption, preventing deadlock. Lastly, we can require that resources be requested and allocated in a specific order. This eliminates the possibility of circular waiting. There are 2 ways of eliminating hold and wait. The first possibility is that the process requests all the resources before starting. This eliminates the scenario of a process holding one resource while waiting for another. The other possibility is that the process cannot request resources if it is holding any. This would require a process to surrender its resources before requesting any others. Both methods will lead to low utilization because resources will sit idle but be reserved for long periods of time. A process would request everything at the start but not use one or more of these resources for quite some time. Additionally, it opens up the possibility of starvation, because a process may wait forever for the situation where all the resources it needs to be available at the same time. We can also allow preemption to occur. This means that we can take a resource away from one process and give it to another that is waiting for it. Eliminating circular wait requires us to establish some kind of order to the manner in which processes request resources. If processes must always get resource 1 before waiting for resource 2, then circular wait is impossible, and therefore there can never be a deadlock. The problem with preventing deadlock is that it also makes our use of the system resources much less efficient. Our utilization of resources will be diminished, as will our system's throughput. Since we want to maximize throughput and resource utilization and not minimize them, deadlock prevention may not be a worthwhile design goal. There is an alternative that may be more worthwhile. Let's give the operating system prior notice of what resources the process may request. Now we can determine the likelihood of deadlock and avoid situations where we are more likely to encounter it. This is what we mean by deadlock avoidance. A system is safe if the system can allocate resources to the various processes in some particular order and avoid deadlock in doing so. An unsafe state is a state that may lead to deadlock. Not all unsafe states are actual deadlocks. Our goal in avoiding deadlock is to avoid unsafe states. Since safe states cannot lead to deadlock, we can avoid it without incurring as high a cost as we would in eliminating the necessary conditions for a deadlock. Imagine a situation where we have 4 processes that are looking to use some of a system's 15 tape drives. They have all indicated what their maximum needs could be. Although they could request a total of 25 tape drives on a system that only has 15, currently they have only requested 12 tape drives. This leaves 3 tape drives available. With those 3 tape drives, P1, P2, or P3 could finish their work. As each finishes, the drives that they have reserved become available for the remaining processes. Then there will be extra tape drives available that P2 needs, and eventually even the 5 tape drives that P0 needs. Since all the processes can get the necessary resources and run through completion, this is a safe state. If any of these processes were to request another tape drive, the system would not be able to fulfill the request. This means that it is not a safe state. It is possible to use resource allocation graphs to show whether a state is safe or unsafe if each resource has only one instance. In addition to the assignment edges and request edges that we discussed earlier, we add another type of edge, the claim edge. Processes must inform the operating system of the resources that they may request over their lifetime. These potential requests, or claims, are shown as claim edges. Claims are not requests because the requests have not yet been made, but the process has a right to request them if necessary. We will now include them in our analysis. If we have a circuit, there is a possibility that there may be a circular wait. Since there is only one instance of each resource, there is mutual exclusion also, as well as hold and wait and no preemption. This could become a deadlock, although it might not. We will avoid these because without unsafe states, there is no deadlock. In this case, there is a circuit, so we are obviously in an unsafe state. This graph shows a state in deadlock. Like the unsafe state, there is a circuit, but what makes this different is that the claim edge is replaced by a request edge. Now our circuit indicates that all the conditions are present to create a deadlock.